This podcast is brought to you by LMU Munich.
The basic message of Sean's talk was that you replace the ontology of gravity. You replace gravity is, in loose words, space-time geometry represented by Minkowski. Replace it with the relations of objects within the universe. Very roughly speaking, represented by Plato here. So, if you have this relational motivation, and I will give a slightly different relational motivation than what Sean did. Because for me, all I'm looking at is, if I want to describe the entire universe as a dynamical system, then by definition there's no external reference structure. And then I want to take that seriously as a motivation for my theory. Then Sean already introduced the ADM formalism as geometrodynamics, describing gravity as how space-time geometry starts to build up when you evolve it forward in time, when you evolve an initial value problem forward in time. But that has, what Sean didn't focus so much about is that inextricably entangles the choice of foliation with the choice of gauge with time evolution. So and if you want to be consistent with your gauge symmetry, you cannot simply pick out one of the Hamilton constraints, one of the ADM constraints, and call it a Hamiltonian, and call the other the rest gauge generators. And the reason for that is because then your constraint algebra does not close anymore. You can, no matter which one you choose, you can always generate a Poisson bracket that this one is generated on the right-hand side. So you have to keep it as a constraint. But of course, by this trick that Sean was showing here, you can disentangle gauge from evolution by fixing a particular foliation with a particular condition. And then the construction of shape dynamics is unfixing that gauge to a different gauge symmetry, to spatial conformal invariance. And with that, you have destroyed space-time. There is no left over of space-time in this description of gravity, but because gravity is now just evolution of spatial conformal geometry. And then that brings me to the main part, the main message of my talk. If you have no space-time, if it's not fundamental to the description of the theory, why is the illusion of space-time generated from within every solution, or within virtually every solution? Why is it such a generic thing that we see in the description of gravity? And so I have to explain to you why scales, unit, and space-time are such a good description, at least for physical observers, at least if I'm a local subsystem in which I can define my reference scales and in which I can define my clocks and rods as physical objects that evolve together with gravity. For these, I have to explain why do they behave as if they were in a space-time. So the relation and motivation, I already said most of that in words. There is no, by definition, there is no external reference structure to the universe. If the universe is everything, I have to do that. I have to describe it as a whole. To make that simple statement very precise in gravity takes a lot of time, but you can get the conceptual idea by looking at the Newtonian in-body problem. And if you look at the Newtonian in-body problem, so the standard, so you have a kinetic energy, a potential energy, and you build your Hamiltonian as the sum of them, then you see that if you want to have energy in the in-body problem, total energy, then that introduces through the back door a unit of time, because it gives essentially a particular decay constant. in your theory. If you want a linear momentum, a total linear momentum, you need a definition of origin, of coordinate origin, with respect to which you measure that. If you want angular momentum, you need a particular frame in which you reference that, in which you evaluate that angular momentum. So you can imagine that you cannot describe the n-body problem completely relationally unless you have energy zero, linear momentum zero, angular momentum zero. But if you restrict yourself to that, then it turns out that it's actually possible to describe the n-body problem purely in terms of its intrinsic configuration without reference to any external structure. And here I just drew 3 particles, and that's Julian Barber's favorite thing, to look at the 3-body problem and explain quantum gravity with the 3-body problem. So here I just show you 2 shapes that are given by instantaneous shapes that are the configurations of 3 particles. And in between I show you the change of shape that is given by that. And it turns out this triangle here has 2 angles, theta and phi. And in a particular parametrization, I will give you a nicer picture of that on the next slide. There is a Hamiltonian that describes precisely that type of change of shape. And it's completely in terms of these intrinsic quantities. And it's dimensionless and scale invariant, a dimensionless and scale invariant description that just describes the change of shape of this.
When you say the Hamiltonian, what are the interactions we're talking about?
The Newtonian interaction.
Newtonian gravitational interaction?
Yes. So what it turns out is that the configuration space for these triangles has the topology of a sphere, and that's what's drawn here. The north and south pole on that sphere are the equilateral triangles, and on the equator here are collinear configurations of triangles, so degenerate triangles, and north and south pole are just opposite orientation equilateral triangles. Then here on these ridges that are yellow, they are the isosceles triangles. And here these deep blue regions are needles, are basically when 2 particles come very close together when measured in units of the distance to the third particle. And so now the intrinsic, so now on the left I show you a typical solution of the energy zero Newtonian n-body problem with angular momentum zero, linear momentum zero. So this is R6, and I projected it down into R2 by using different colors. So you see here the blue and green particle come in, they interact with the red particle that comes from up, and they form a new Kepler pair, and it shoots out this way, and the blue particle shoots off that way. And the message, the important message of this slide is you can describe that completely you don't need Newtonian space to describe that. You can describe that completely within the terms on shape space in terms of the shapes of these triangles. And what will happen is you start out here where 2 particles are close together. They change their shape like a Kepler pair. They have approximately periodic motion. Then when they come close to the third particle, you will be pushed out of that valley of the shape potential. There will be some violent interaction that can take place all over the sphere. And then eventually the trajectory will fall back into one of these needles because 2 particles will come close together, they will form a Kepler pair, and 1 particle will, by energy conservation, be shot off. And that's what's depicted here. So Sean gave you already some background in canonical dynamics, and I don't know about everyone's background in canonical physics, in the canonical description of dynamical systems. So very simple. You have a harmonic oscillator, you have a phase space, and your Hamiltonian generates a vector field on phase space. And the integral curves of that vector field are your solutions to that. So that's the simplest thing that you can have, but most of the time we are actually dealing with constraint dynamics. For example, a particle constrained to be in a particular surface, say this surface that I drew here, which can be described as some function of the coordinates vanishing. But then if the particle is confined to the surface, also its momentum normal to the surface has to vanish, so it cannot get out of the surface. That means there's automatically a second constraint to that. These two constraints will keep the Hamilton vector field within the surface by choosing particular values for the Lagrange multipliers, particular forces that keep the dynamics on the constrained surface. And that's what I drew. That's why the Hamilton vector field is tangent to the surface. I hope you can see that from that plot here. So if you have a gauge theory, and Sean already introduced that, then the constrained surface itself is foliated into gauge orbits. So this is what I indicated with these dark red lines. Actually, the entire constrained surface is foliated. I just drew some example ones. And due to an argument by Dirac, basically that the initial state of the system completely determines the dynamics at all later stages of the canonical problem, you have to identify the entire gauge orbit with the state of the system. You cannot just simply say a point on the constrained surface is a state. You have to take equivalence classes of these points, the entire gauge orbits. And then the physical evolution, because it's already a constrained system, the Hamilton vector field has to be tangent to that constrained surface. It cannot go out of it. So now, what Sean was also saying is, if you have a gauge theory, you can gauge fix it and treat it after gauge fixing as if it was a normal constrained system without gauge symmetry. So you impose a second set of conditions. So I called on the previous slide, I didn't say that, I called the constraints the gauge generators chi. So I impose condition sigma, blue, indicated by the blue surface, that pick out a unique representative out of each orbit, out of each constrained orbit. And then individual points, of course, by construction represent physical states of the system. So now here comes the problem that I mentioned, and Sean also mentioned in passing. And this is actually 2 + 1 gravity. If you do 2 + 1 gravity, it's a particularly nice system because the geometry in 2 + 1 is locally conformally flat. So all I have to tell you to specify geometry is what the conformal factor looks like locally. So I look at one space-time, and I look at the different intrinsic geometries when I do two different slicings of the same space-time. So from the point of view of GR, they're the same solution. For that, later I will use the torus. Those plots are fantasy plots, actually. They're not anything particularly meaningful. I just used some random numbers to generate these plots. I don't even know whether this space-time is a solution to Einstein's equation. Just to illustrate the point. The point is that here I just drew two different successions of spatial geometries that correspond to the same space-time, and that's the gauge problem, that you have to identify this succession of spatial geometries with that succession of spatial geometries, and you have to identify that they are the same space-time. And there is no simple mathematical tool to do that. So, and this is what I said, GR entangles evolution and gauge inextricably for the reason that I mentioned before. And if I do the same thing as what I did a couple of slides before, where I have the Newtonian representation and the shape space representation, if I now look at one solution and I look at different slicings, and I have this infinite dimensional superspace, this space of all of all two geometries. It's an infinite dimensional space, so I draw many axes here, and so these successions trace out many different curves. And in fact, I would have infinitely many curves. I just drew 2. And those are real fantasy curves. I just drew them by hand. But you get the point. So now comes the symmetry trading. And this is if I have a gauge fixing surface now that itself foliates into gauge orbits. And that's the key thing. Then I can look at this intersection where the physical states live and where the physical dynamics takes place. Once I can look at it as coming from this gauge theory, which in the case of GR or ADM would be a gauge theory of a space-time diffeomorphism gauge theory. Or I can look at it as coming from this constrained surface. And then I have, in the case of shape dynamics, I describe gravity as evolution of spatial conformal geometry. Now this is what is indicated here. Actually, and Sean made this point very clear, this intersection still contains one-parameter families because the CMC condition, he wrote it right here, doesn't say that trace pi is a particular number. It says that it's just a spatial constant. And now I look at these one-parameter families at the intersection here, and if I look at them with my red glasses on, or actually with my blue glasses on, so I just see the red, then I look at them and see, oh, they're space-times foliated with CMC surfaces. But on the other hand, and this is why it's important to do 2 + 1 and on the torus, because I can draw the Teichmüller space for the torus. Actually, this is not the best drawing. Those of you who know what a Teichmüller space, what the boundaries of Teichmüller space look like, they see that I missed an edge here. But now you can see these space-times foliated with CMC surfaces can be looked at as being just geodesics on Teichmüller space. So on the space of two-dimensional conformal geometries on a torus. And that was actually noticed first by Moncrief in 1988 in a very famous and very nice paper. I mean, even people who are not interested in gravity find that paper nice and interesting. So here I have the summary, and this is exactly what Sean was saying, except that I do one thing differently. I use the Hamiltonian that Sean used. So on the GR side, in the ADM formulation, the Hamiltonian is just a linear combination of constraints. I like to think about the Hamiltonian as the York Hamiltonian, which is the on-shell value of the spatial volume, expressed as a function of the conformal metric, the trace-free part of the metric momenta, and York time, which is 2/3 of this mean of trace pi here. And if you introduce this time variable, then it turns out that you can forget about this part and you can impose full conformal invariance. But you have to identify that this part is now a time variable and pure gauge. So if I do that, then I have completely done away with space-time. But why do we experience space-time? So, of course, my approach to that is, as I indicated before, is operational. You have to evolve matter together with conformal geometry. And so you have to satisfy certain conditions. If it's quantum matter, you have to get into a semi-classical regime for this procedure to work first. But then, even if you're in a sufficiently classical regime, you have to satisfy conditions such that you get locally weakly isolated or just weakly interacting subsystems that are very stable by themselves. And so they can actually, this is the same as what you say in GR, you need low curvature, you need to be in a low curvature region where the curvature radius of your space-time curvature has to be much smaller than the typical, has to be much larger than the typical size of the system that you use to explore space-time. And something similar has to happen here. Interestingly, the n-body problem that I introduced at the beginning already exhibits something analogous. So if I take the n-body problem, I can do something very similar to what I did, there's a similar description. What I showed you for 3 bodies works for arbitrarily large n. And in a generic solution, there will be a time where all particles strongly interact. But then, if you satisfy the energy zero condition, then the system will split up and will form local clusters. And most of these clusters will, after a long time, contain just 2 particles. So they will form Kepler pairs, most of them. And then these Kepler pairs, they provide you, because they become more and more isolated, they fly apart. They provide you a local clock, because they have an orbital period, a year, and a semi-major axis, an astronomical unit. And so you have clocks and rods and a direction, so a frame of reference, provided for free in each solution. And if I describe the dynamics of the nearby particles in terms of the clocks and rods of this, they look like approximately inertial motion described in these units here. But of course, it's just a change of units if I'm an inhabitant of that solar system. I use a different year, I use a different astronomical unit, but the same dynamical law describes their point of view, and so on. That goes all over. So it looks like here I have not put in Newtonian at any stage. I have described the dynamics completely in terms of the change of shape of the system, of the relations within the system, the dimensionless relations within the system, just the angles between particles. And yet I still see, at the late stages of evolution, I still see something that looks like a Galilean space-time coming out of that in my solutions, if I make an appropriate choice of clocks and rods, of physical subsystems, and if I use them as clocks and rods. It's actually an interesting, there is a lot of mathematical physics work from the 60s and 70s that explored energy, well, positive and energy zero solutions to the n-body problem. And actually, the only difference, the strongest statements hold for the energy zero case, but the only difference between positive and zero energy is that in positive energy, you can have something that looks like a freeze-out of shape. Basically, all particles, there can be enough kinetic energy in expansion that the system just flies apart and goes into a constant shape, and just seems to stop, the evolution just seems to converge to a point in shape space. Yes, there are. This is actually a good point. The these long-term stable configurations, they're actually critical points of this shape potential. So it turns out that scale is completely irrelevant for determining what these long-term stable configurations are. Because if you're at a critical point of that, for a long time, you will get periodic motion near one of these critical points. And then depending on global conditions, actually there is more to that story. I can say that, I can talk about that afterwards. Effectively, it's a nice thing. This Hamiltonian has a particular time dependence, like the York Hamiltonian does for the closed case in GR. And this time dependence effectively introduces a friction term into the equations of motion. And so you have relaxation into this equilibria, but then some of these equilibria are not stable. So if you're close to that, if you're close to a critical point of this potential, you will stay there for a very long time, but then eventually friction will set in and you will start to slide down into a deeper region of the shape potential. And then you get trapped into a local minimum. And actually there are no local minima, there are only saddle points and global maxima. So, or these steep valleys, which are when at least two particles come very close together. So the other part of the illusion of space-time has to do with the emergence of units. And so about this thing that is here, we have good indications for full GR, how to do these things in shape dynamics. For this part, I only have toy models. I only have particle toy models that illustrate what I want to do here. So the question is, if I start out, like Sean was motivating, with a completely scale invariant and dimensionless description of my system, as I did on the previous slide, then I have to explain why is the description in terms of units so useful. I mean, why is dimensional analysis one of the most useful things in physics? And the operational answer to that is, well, you have to evolve quantum matter together with conformal geometry. Well, for GR, that's a conjecture. For the n-body problem, I can show you roughly, of course on one slide I cannot show you the details. There is a Schrödinger equation that is a natural operator ordering choice for this Hamiltonian here that I have there, and it's self-adjoint, and it is a nice Hamiltonian. It's something that you would accept as a Hamiltonian. And then you look at the time evolution of this wave function. And it turns out that if certain conditions are satisfied, then at late times the system will develop atoms with an effective mass, so closed two-body bound systems, and with an effective coupling constant. And this effective mass and the effective coupling constant are derived from the state of the rest of the universe through the energy zero condition that is preserved by this Hamiltonian. But of course I don't know when I look at this Hamiltonian. I have defined the system to be that. I have not defined the system to be Newtonian.
This is you're not only assuming zero energy, you're also assuming zero angular momentum.
Yes, also zero angular momentum. Yes. Yeah. But then, of course, I can use once these atoms pop up, I can use their effective mass to define my kilogram. I can use the Bohr radius of these effective atoms to define my meter. I can use the Rydberg constant to define a second, and so on. So I have, and in a very similar way, I mean actually in exactly the same way, just that you have now just that you have now Kepler pairs that all look the same. You don't have to make a change of units. You don't have to change your astronomical unit and definition of year when you go from here to here, because they're now the same, or effectively the same. You have a spontaneous emergence of a Galilean space-time in that system. So this is how the illusion of space-time is appears, and this is Julian Barber likes this sentence: the props that hold up space-time, how they pop out. So if I could do it with all rigor, then I would have a picture in which I have atoms forming on my conformal geometry. I evolve quantum matter together with conformal geometry. These atoms would give me a local scale, because they have a local Bohr radius. So I can define a local scale. This is what I indicated by these arrows here, that I know how large, how much distance there is, the unit distance in the main directions that I have here. And then their evolution also gives me a unit of duration that I have between. So I can, from this succession of the evolution of geometry with matter, I can deduce local scale and local duration from that, and generate the illusion of a space-time from within this illusion itself. So that's what I wanted to talk about here. That's just a summary. And here is one of that's an Einstein quote of his autobiography. And it illustrates this point this relational point that is missing in the construction of GR. And that in particular Julian Barber has been taking very seriously and motivated us and a couple of other people to work on this. So thank you for your attention.